we come back to finish our look at probability from section 8.4. Moving on to some new looks at probability. We're just going to further the concepts we've already started on by focusing on some set operations and their symbols. So E and F are separate events for the same sample space. Then we can say that E intersect F occurs when both E and F occur. So this symbol is my symbol for intersection. E or F occurs when E union F occurs when E or F occurs. And then this is complement. So when you have an apostrophe, that means complement. It means everything but that event. Okay, you know these words, you know what they mean. Intersection is like the intersection of streets. If you come to a stop sign, if I'm over here, I'm not in the intersection, but if I'm here, I am in the intersection because I am in both streets, part of both. So the intersection is the and. You have to be in both sets to be in the intersection. Union is his, her, or ours. Marriage is a union. Anything that either person in the marriage brings is now a part of the union. So that is my or. Now it can be in both, that's fine, but it just has to be in one or the other to be part of the union. And then that apostrophe means the complement. It means not E. E complement means not E. Anything except that. Okay, so let's think about this. Consider rolling 2 standard dice, regular dice, and finding the sum. Well, what's my sample space going to look like? If I'm finding sums, the smallest value I can roll on each of those dice is a 1. So the smallest sum would be a 2. That would be my smallest roll. I could roll a 3, 4, 5, 6. What's my largest possible roll? Well, the largest number on each die is a 6, so the largest sum would be a 12. Now, how many different outcomes are in that sample space? Well, if I look at pairing them up, I can roll on my first die, I can roll 1, 2, 3, 4, 5, or a 6. On my second die, I can roll a 1, 2, 3, 4, 5, or 6. So if I think about setting this up like a grid so that I'm filling in possible outcomes for my sample space, how many different outcomes fit in this grid? Well, I've got 6 rows going this way, 6 columns going this way, so it is a 6 by 6 grid, which means there are 36 total outcomes in my sample space. Now these are the only different outcomes, the values 2 to 12. Everything is going to fit between 2 and 12. My smallest sum is 2, my largest sum is 12, and then everything else is going to be in there somewhere in the middle, right? But there will be 36 total outcomes in my chart. Out of these outcomes, name an event where the probability of that event is 1. So the probability is a sure thing. Well, we could list a lot of different options here. One I have written down is the probability that my sum is less than 13. That is an event that is a sure thing. My probability is 1. The sum is less than 13 because every sum is less than 13. What's an event whose probability is going to be 0? So it can't happen. Well, let's do it this way. Event would be the sum is what? Greater than 12? Because 12 is the largest possible value, so that one can't happen. Name 2 events that are complementary. Again, a lot of different answers here. Let's say that my first event has a sum less than 7. What would be the complement of that? Well, sum less than 7 would be 2 through 6. The complement of that is going to be everything else. So that would be sums greater than or equal to 7. That includes all the possibilities. All right, what about this? given that event A says my sum is even, event B says the sum is odd, and event C says I have a sum that is less than 8. We just want to, we're not giving probabilities here, we're just describing. Read that symbol. That's my intersection symbol. It means and. So this would be the event that is a sum that is even and odd. A sum that is even and odd. What about this one? Well, that is my union. Keyword is or. So that would be sum that is even or odd. Right here, this is going to be odd and less than 8. Sum that is odd and less than 8. This one would be sum that is odd or less than 8. I'm going to change that to my inequality symbol. Sum that is odd or less than 8. So my keywords are important. Out of these 4 compound events, which one is a sure thing? I am certain that it's going to include everything in my sample space. Well, my sure thing is going to include everything in the sample space would be a sum that is even or odd, A or B. Which one of these compound events is impossible? So this one has a probability of 1. Which one is going to have a probability that is 0? It's impossible. Well, I don't have any numbers that are both even and odd, so this one, A and B, is an impossible event. Which events are complementary? Notice it doesn't say compound events. So if I look at A, B, C, which of the 2 are complementary events? Well, every sum that is listed is either even or odd, so A and B are complementary events. Without doing any calculations, what would we know about the probability of A and B, as well as the probability of, oh, I said that wrong, probability of B and C, as well as the probability of B or C? Which one of these is going to be larger? Well, or is going to include more opportunities. And I drew my, I hope you guys were catching it and hoping I did. Less than 8. My inequality symbol was backwards here. I happened to catch that they didn't match. These are both less than 8. So glad I got it before we turned the page. Okay, so back to our question. We're looking at these 2 compound events, B and C, B or C. This one is going to have a higher probability. Will either one of them have a probability of 0? No. Either one of them have a probability of 1? Do they include everything? Well, let's look at our list and see. B and C, the sum that is odd and less than 8. So these are my sums. Less than 8, that's my list that's less than 8. Out of those, odd numbers are 3, 5, 7. So that would be 3, 5, 7. What about odd or less than 8? Well, if it can be odd or less than 8, I get to include everything in that list. 2, 3, 4, 5, 6, 7. So the or has a higher probability. There's more options in that sample space. These can both happen, so neither is impossible. They do not include the entire sample space. So the probability of either one of them is not 1. Oh, which one will be greater? That one is going to have a greater probability because there are more outcomes in that option. Okay, let's go ahead and look at the next. That's a question you may have come up with more answers than what we listed out, but let's go ahead and look at the next page and move on. Disjoint events. Disjoint events are events whose sample space is empty. So if A intersect F is the empty set, that means that they do not share anything. So this is an example where these do not have an intersection. So we would say that these two events are disjoint. Now, this is E and this is G. If you can see it, E includes the elements 4, 5, 6. G includes the elements 1 and 2, and 3 is out here in the universal set. So my universal set is going to be 1, 2, 3, 4, 5, 6. So all the numbers on a regular standard die. But E and G don't share anything. There are no elements that are common. So there's no intersection. So I can say that those two are disjoint. The probability of E and G is 0. Of the events A, B, C on the previous page, which are disjoint? So if we look back at our last page, out of these three, which don't share anything? Well, A and B can't be both even and odd at the same time, so those are disjoint events. All right, basic probability principle. This is for theoretical probability. Remember, we have theoretical and empirical probability. When we're working with this basic probability principle, we're focusing on theoretical probability because we're comparing the probability of an event to the number of things in the sample space. The number of elements or the number of outcomes in the event compared to the number of outcomes in the sample space. We already did this in the last section. Now, caution, the basic probability principle applies only when the outcomes are equally likely. So if we have a situation where, like that geometric probability, where one thing is weighted heavier than the other, this probability principle isn't this simple. But we're going to be focusing where events are equally likely. For example, rolling a standard die. When I roll a single fair die, the probability of the events are equally likely. This is what we've been talking about. My sample space are going to be those numbers 1 through 6 because those are the values on each side of the die. If this is my event, getting a number that is a multiple of 3, the probability of that event, well, 3 and 6 are multiple of 3, so that's 2 out of 6, or 1/3 is that probability. Not getting a number that is a multiple of 3 would be the complement of this event. So if the probability of getting a multiple of 3 is 1/3, the probability of getting a number that's not a multiple of 3 is going to be everything else, 2/3. The other 4 outcomes out of the 6. Getting a number, let's say this is event F, getting a number greater than 4. Well, what numbers are greater than 4? Just 5 and 6. So the probability of that event F is going to be 2 out of 6, or again 1/3. Getting a number less than 4. Now we need to decide if these two events are complements. Greater than, less than, what about equal to? Numbers less than 4 are these three numbers. I've just left 4 out. So I can't call this F prime, I can call this event G. The probability of getting a number less than 4, event G, is going to be 1, 2, 3 out of 6, or 1/2. So be careful, pay attention when you're figuring out if events are complements of each other. My addition rule for probability says that for any events E and F from the same sample space, the probability of the union is equal to the probability of the first event plus the probability of the second minus the probability of the intersection. Alright, so this is my union symbol, keyword OR. This is my intersection symbol, keyword AND. Alright, let's do some examples. Now, I am not much of a gambler, so I have never played roulette. Apparently there are different types of roulette wheels. I had to do a little research for these problems. When playing American roulette, The croupier, who spins the wheel, spins a marble that lands in one of 38 slots. So there's 38 slots on the roulette wheel. The slots are numbered 1 to 36 with 2 additional slots labeled 0 and 00. So I've got 0 and 00 on opposite sides, and then the rest of them are my integers 1 through 36. 0 and 00 are green. Half of the rest are red and half are black. So if I've got 38 total slots, 2 are green, and then the other half are split. That means half of 36 is going to be 18, right? So I've got 18 red and 18 black. Find the probability that the marble will land in a red slot or an even number. So we got to pay attention to what are my red slots, what are my even numbers. So probability that it will land on red or even. I can use my probability addition rule. So I need to know the probability it will land in a red slot, add to that the probability of my even number, and then subtract the intersection of the two. The red evens, I'm going to have to subtract that. Well, how many are red? We just said that we have 18 out of 38 slots that are red. How many numbers are even? We are not going to count 0 and 00 as even on the roulette wheel. 0 is actually counted an even number, but again, research, we're not counting these as even. So I'm just thinking numbers 1 to 36. Half of those numbers are going to be even numbers. So that's 18 out of 38 slots. So together that gives me 36 out of 38. But some of these I've counted twice because some of these evens are on red. So I need to go around the wheel and I need to figure out how many of my even numbers are on red slots because I've counted those guys twice. So if I start up here at my 00 and work my way around, 12 is even red, 18 is even red, 16, 14, 30, 32, 34, 36. Those are my even red slots. So that is 1, 2, 3, 4, 5, 6, 7, 8 that were counted twice. Well, 36 minus 8 gets me to 28 out of 38 slots that are red or even or both. I can simplify that. Those are both divisible by 2 for sure. If I divide by 2, I get 14 over 19, and yep, that's lowest terms. Okay, let's walk through the next one. Find the probability that the marble will land in black or a number that's divisible by 3. So we're interested in probability that it's black or divisible by 3. Black or divisible by 3. So we need to see the probability it will land in a black slot plus the probability that it will land on a number divisible by 3. And then I need to subtract where those two things are the same because that's my intersection. I don't want to count those twice. Well, I have 18 red, 18 black, so the probability it will land in a black slot is 18 out of 38. What about numbers that are divisible by 3? I need to look at my multiples of 3 that are between 1 and 36. And the easiest way, I think, to do that is just to count them up. 3, 6, 9, 12, 15, 18, 21, 24, 27, 30, 33, 36. That's 12. I've got 12 numbers that are divisible by 3. Now, which of these are on a black slot? So my multiples of 3, numbers that are divisible by 3, I'm looking at 3, 6, 9, 12, 15, 18, 21, 24, 27, 30, 33, and 36. Those are my numbers between 1 and 36 that are divisible by 3. So I need to see which ones of those are on the black, and I think I may need a color that's going to stand out a little better. So let me get a green out here. So I'm looking for black multiples of 3. 6 is a black multiple of 3. 33, not 28, 15, 24, I think that's it. 1, 2, 3, 4. Yeah. So 4 out of the 38 are in the intersection and have to be subtracted out. 18 and 12 is 30 minus 4 is 26 out of 38. Those are both even, so if I simplify by dividing by 2, I get 13/19 is my probability. All right, excellent roulette wheel practice. Let's look at the next example. Now this one sets up a Venn diagram for us. Fatal vehicle accidents. Let A represent the probability that the driver was age 24 or younger. So this is the driver is less than or equal to 24 years old. Let B represent the probability that the driver had a blood alcohol content of 0.08% or higher. Okay, so this is age. A is age. B is blood alcohol content. We need to find the probabilities. Now notice it's got probability of A would be these two regions. Probability of B would be these two regions. I have my probability of my intersection, and I have everybody else. This is the population that is in an accident that does not fit either or both of those two categories. So 0.68 or 68% of accidents are not going to be young drivers or drivers with a blood alcohol of 0.08 or higher. Find the probability that the driver had a blood alcohol below 0.08. Well, this is greater than or equal to 0.08, so that is going to be 1 minus the probability of whatever B is, because we're looking for the probability of the complement of B. So I need to add these two together, and when I add these two together, I get 0.1648. So my probability comes out to be 0.8352. Next question. Find the probability that the driver is 25 years or older. So A is less than or equal to 24, so we're looking for the probability of not A, everything outside of A. So I can find the probability of A and subtract it from 1 again, or I could add these two probabilities up, because that is, this blue circle is A, everything else is not A. That's those two regions, 0.68, 0.1318, gives me a probability of 0.8118. All right, let's keep going. Let's find the probability that the driver is less than or equal to 24 and has a blood alcohol content that's high. So that's the intersection of these two. We're looking for the probability of A and B. That's already found for us. It's right there in our Venn diagram. And then finally, the probability that the driver is older than 24 and has a lower blood alcohol content. So doesn't fit in this one, and also does not fit in A and does not fit in B. Well, if it's not in A, it's not in B, it's the rest of these guys out here in the union. So the probability of not A and not B is that 0.6800. All right, so a lot of this is I do it mathematically, I reason it through, I cover things up because I like pictures, I like to illustrate what I'm looking at. All of those things together make that easier. Okay, last page we're going to talk about odds. Odds are related to probability, but instead of looking at the total, we compare odds in favor to odds against. The odds in favor of an event are defined as the ratio of the ways that event can happen to the ways that event won't happen. Now, I can make this a little more simple. Let's look at some examples. This will clear it up better. Find the odds of the event occurring from the given probability that a bachelor's degree recipient in 2014 majored in a specific discipline. So, here's the probability that someone who got their bachelor's in 2014 was a natural science or math major. That probability is 2 out of 25. What are the odds of that happening? Well, if the probability is 2 out of 25, the odds are 2, that's how many got that type of degree, compared to the rest of them. Well, if there's a total of 25, the rest of them are 23 other students. So my odds in favor of having this degree, if I graduated with a bachelor's in 2014, are 2 to 23. Not out of, but compared to. This is the way they stack up. 2 students would have this type of degree compared to 23 students that had a different type of degree. What about a social and behavioral sciences degree? Well, their odds are a little better. 3 compared to 3. For every 3 students who got this kind of degree, how many got a different kind of degree? Well, not 20. I already counted 3 of those 20. 3 to 17. Now these are odds in favor. If I wanted to find odds against, I'd just switch it. Okay, a single fair die is rolled. Find the odds in favor of getting these results. The odds in favor of rolling a 2, 3, or 4 compared to the other outcomes. Well, there's a total of 6 outcomes, right? Here are 3 of those outcomes. So I'm going to compare that to the other 3 of the total 6 outcomes. I could also write that as 1 to 1. If I'm rolling a single fair die, regular die, standard die, what's the odds of getting a number greater than 5? Well, on that die, 6 sides, how many numbers are greater than 5? Just 1, right? Only a 6 is greater than 5. So the odds in favor of rolling a number greater than 5 are going to be 1 to the other 5 outcomes. Finally, convert the given odds to the probability. So here we were going from probability to odds. Now we're going from odds to probability. If I'm given the odds that a tax revenue comes from sales and gross receipts, those odds are 7 to 13. What's the probability of that event happening? Well, 7 are the number of outcomes where it happens that way. What's the total number of outcomes? I need to add those up. 7 out of 20. What are the odds that tax revenue comes from corporate income tax? Well, the probability of that event happening, 37 ways out of how many total outcomes, income streams? Well, if I add that up, I get 1,000. All right, so that is our quick look at odds.